que se conectan les damos la bienvenida al webinar Lower Limb Assistive Devices Informed by Human Biomedical Models, organizado por los departamentos de Ingeniería Mecánica, Ingeniería Biomédica e Ingeniería Eléctrica y Electrónica de la Universidad de los Andes. Hoy nos acompañan los profesores Luis Felipe Giraldo, Cristian Javier Cifuentes y Carlos Francisco Rodríguez, y nuestra conferencista Cara Gonzalez-Welker. Cara es doctora en bioingeniería de la Universidad de Stanford, Estados Unidos. Actualmente es profesora asistente visitante de la Universidad de Colorado y becaria postdoctoral en la Universidad de Michigan. Su investigación se encuentra en la intersección de la biomecánica, la áptica y la robótica. Recuerden que al final de este webinar tendremos un espacio de conversación y preguntas. Pueden escribirlas en el chat o levantar su mano y activar su micrófono. Sin más preámbulos, le doy la palabra a nuestra conferencista, la doctora Welker.
Ok, gracias. Muchas gracias por tenerme hoy y lo siento, pero voy a hacer esta presentación en inglés porque es mejor que mi español y también no sé algunas palabras científicas en español. So today I'm going to be talking about lower limb assistive devices informed by human biomechanical models. And I want to start with this introduction, just saying that human movement is amazing. So I think this photo does a great job illustrating kind of all the intricacies of how we move as humans. And so when you think about all the processes involved in walking on a path like this, it includes seeing the ground ahead of you, predicting how and where you should be stepping on the path, and sending motor commands to your hundreds of muscles, which then might get updated if a rock is loose under your feet, for example. And it's pretty amazing that we can do all this while carrying a 30-pound pack and still be relatively confident that we aren't going to fall off the path into a lake. Human neuromuscular control is also complicated. So there are many complex steps involved from the conception of thinking about moving to actually moving. And this movement starts with input from our brain, but this is extremely complex and not fully understood. And next, these commands are sent to our muscles. So we have a better understanding of the role of different muscles in movement. And it involves this complex muscle tendon dynamics and the geometry of our bones. And then all these forces get combined to produce skeletal dynamics and joint moments at your different joints. And that produces some movement. So if we are trying to develop assistive devices like this robotic knee ankle prosthesis, for example, we have to keep in mind that the control of the robotic device is complicated, but also we're interfacing with this very complex human neuromusculoskeletal system that is also complicated. So I'm going to be talking today about two examples of assistive device control from biomechanical models. The first is a passive running device designed from a simple model that utilizes complex neuromuscular control. And the second is using human movement data to optimize continuous control strategies for a robotic prosthesis. And I'll start with this first one and give a little bit of a background on running biomechanics. So this figure depicts the typical motion of the human body over time while running. And I've noted some key points such as heel strike when the foot initially comes in contact with the ground, as well as toe off when the foot leaves the ground. And because running is cyclic, you'll notice that the motion starts and ends with heel strike. So human running can broadly be separated into the stance phase when the foot is on the ground and swing phase when the foot is off the ground. And it's estimated that more than 80% of the cost of running is associated with supporting your body against gravity and propelling your body forward, which occurs during the stance phase, while only about 7% of the cost of running is associated with swinging your legs back and forth in the swing phase. And this other category has to do with costs such as side-to-side balance. So because the majority of the cost of running is associated with the stance phase, devices previously designed to assist in running have targeted this larger cost with some success. So the first device to reduce the metabolic cost of running was developed in 2017 and assisted in hip extension with these off-board motors that the user didn't have to actually carry the device. The Nike Vaporfly shoe has been validated to save energy with its carbon fiber plate and foam insoles that return energy to the runner. And then finally, the group that made this initial device was able to move the motors on board so that the user carried it with the same mechanism of action. And all these devices reduced the energetic cost of running by about 4%. But myself and colleagues working on this project wondered if we could build a passive device that assists in leg swing to reduce the energetic cost of running. So in human running, you can model the legs as a mass on a pendulum swinging back and forth with this joint representing the hip. And based on this model, we hypothesized that a passive spring could store and return energy as the legs swing back and forth instead of the hip muscles shown here in red, expending energy to both brake and then later accelerate the legs. So we could have built a hip-mounted torsional spring, but we decided the easiest way to test this was to simply attach an elastic band between runners' feet, which we called an exotendon. And after performing some initial simulations to determine the effect of stiffness and resting length on this band on metabolic cost, and some pilot tests to ensure that runners could still move their legs and not trip, we decided on a stiffness of 125 newtons per meter and a length of 25% of the user's leg length. And we attached it directly to the shoelaces. So here's a picture of the exotendon on a runner. And you can see that as the legs move further apart, the exotendon engages and provides braking and then accelerating forces. And when the legs are close together, it's not engaged. So the first question we wanted to test was the efficacy of this device. So we brought in 12 recreational runners to run on a treadmill, both with and without the exotendon. And we performed 4 comparison trials over 2 days, each one consisting of running for 10 minutes without the exotendon, represented here in gray, and 10 minutes with the exotendon, represented here in blue. And for each trial, we did a comparison between these two conditions. So we collected oxygen input and carbon dioxide output with this mask here to determine the energy cost or metabolic effort, as well as data from inertial measurement units and 2D videos to determine stride frequency. And here's a video of one of our subjects running both with and without the exotendon. So you can compare the changes in her gait, and so that I can prove to you that you can run with a rubber band tied between your feet. So here are our results from this experiment. So in this plot, more negative numbers on the y-axis correspond with more energy saved in the exotendon condition compared with running without the device. And all 4 comparison trials are plotted. And each of these gray dots is one subject. So you can see that initially there was no group net benefit of the device. Actually, about half of the subjects, it costs more energy to run with the exotendon than without it. But over time, users adapted until the 4th trial, when all users were able to reduce their energy cost by an average of 6.4%. And from our measurements of stride frequency, we noticed that all participants ran with an increased stride frequency compared to their natural running condition, shown in dark red, compared to exotendon running, shown in light pink. So from this experiment, we concluded, first of all, that a simple passive device targeting leg swing can reduce the energetic cost of running by about 6.4%. And this was pretty amazing because it outperformed all passive and active devices at the time that had only been able to achieve about 4% savings. We saw that some adaptation time was needed for all users to benefit from this device. And we also noticed that all users adopted an increased stride frequency. But this experiment also left us with some open questions. For example, why did users increase their stride frequency using this device? And we were also curious about the device's mechanism of energetic savings. So to answer these questions, we ran a follow-up experiment to determine the mechanism of this device. So we brought back 4 recreational runners from our initial experiment, and we ran a series of trials where we ran both with and without the exotendon at different stride frequencies while we measured their energy cost. So to determine what these stride frequencies were, we first measured their natural chosen stride frequencies, both with and without the exotendon, as well as the percent change between the two, which is represented by a delta here. We then ran 3 additional trials for each exotendon condition, shown here in blue, and natural running condition, shown here in gray, where we enforced stride frequencies with a metronome. And these enforced stride frequencies corresponded to their kind of initial chosen stride frequencies, as well as both a slower and faster stride frequency, with these specific values determined by this delta that we originally calculated. So in addition to metabolic effort, we also measured lower limb kinematics with optical motion capture and lower limb kinetics with an instrumented treadmill. And we were able to input this into an open sim model, so we could determine the joint angles and joint torques needed to run both with and without this device. So here are our metabolic results from this experiment for all the trials with enforced stride frequencies. So for each subject, we fit the points that we collected to quadratic curves and then average the overall results. And on this plot, the y-axis again represents energy expenditure, with a more negative number corresponding to greater energy savings. And the x-axis is the stride frequency during each condition, represented as a change from what the subjects chose in the natural running condition. So this 0 point is the frequency that they chose without the device. And these data points in red is natural running, and again, light pink is exotendon running. So as we can see, subjects adopted an increased stride frequency in order to save energy, because the energetic cost of running at this initial 0 stride frequency would have resulted in no net energetic savings. We also compared the biological hip joint torques in stance and swing. And we expected to be able to reduce the net biological hip moment in swing, because this is what we designed our device to do. But we also saw that it was reduced in stance as well. So how do we explain this? So running speed is determined by stride frequency multiplied by stride length. And if we bring up this chart of associated running costs one more time, you'll remember that we were targeting assistance in leg swing with this device. By providing assistance in leg swing, the exotendon made it more energetically favorable for participants to increase their stride frequency. And because they were running at the same speed on the treadmill, this resulted in shorter stride lengths, which meant they didn't have to propel themselves forward as far per stride. And this actually decreased the cost associated with forward propulsion, which occurs in the stance phase of running. So by targeting the swing phase, we were able to achieve savings in both swing and stance with this device. So from the second experiment, we concluded that users adopted a faster stride frequency because it did allow them to save energy. And more surprisingly, we found that this device designed to assist in leg swing was also able to assist in stance due to complex adaptation and running biomechanics. So now I'm going to transition from talking about this very simple device that resulted in energy savings from complex adaptations to discussing a control strategy developed for a more complicated robotic device using human movement data. And although myself and my colleagues have applied some similar principles to walking, today I'm going to focus on sit to stand. So motivation for robotic prostheses in general. So there's over 600,000 Americans with a major lower limb amputation, and specifically focusing on sit to stand, people that have passive prostheses rely on their intact limb for the sit to stand and stand to sit motion, which means it takes them longer to transition between these two activity. And they're also asymmetrically relying on their intact limb. And this asymmetry results in high rates of osteoarthritis and lower back pain. So the current state of robotic prosthetic controllers is, so for a given motion such as this, take this stand to sit motion, typically how these robotic prostheses are controlled is researchers kind of subdivide this motion into different substates and kind of determine given rules for when the controller should switch from one substate to the next. And especially for sit-to-stand control, typically we use impedance control, which is given by this equation. So the torque output at each joint is given by a certain stiffness times the difference between the angle of the joint and some equilibrium angle, and then a damping times the angular velocity of that joint. And so these two terms are typically measured, whereas these parameters are typically tuned for that user and that prosthesis. And you may think that tuning 3 parameters is not a big deal, which is true. But for one given substate, these parameters have to be tuned for each joint. So for this, it would be for the knee and the ankle, you would have a different stiffness, a different equilibrium angle and damping parameter. And then this is multiplied by each of these substates. And then because each of these motions are treated separately, for example, from sit to stand, you would have to repeat this whole process over again. So our goal was to create a unified sitting and standing controller for a knee ankle prosthesis from able-bodied data that didn't require manual tuning. So as an input to our model, we had a data set of 10 participants performing sit to stand and stand to sit motions 5 times each. And here's an example of one participant performing one of these trials. So from this OpenSim model, we could output for each joint, the torque, the angles, and the angular velocities over time for each of these trials. And so our next step to develop this controller was converting to the phase domain. And what that means is we wanted one variable to kind of track the progression of kind of where we are in the sit to stand motion instead of having individual substates to break this up. And so we chose the thigh angle as our phase variable. So when a user is seated, kind of the thigh angle is at its maximum, and it kind of progresses monotonically to until 0 when the person is standing. So specifically and the nice thing about this using this phase variable is we can not only go from sit to stand, we can also go backwards from stand to sit as well in one unified model. So specifically for our phase variable, we used this input dictated by kind of this initial sitting thigh angle minus the current thigh angle, and then normalized by this initial thigh angle so that our phase variable was 0 when a person was sitting down and 1 when someone was standing up. So we were able to use this definition to kind of take these trajectories of the joint torques, angles, and angular velocities in time and convert them to torques, angles, and angular velocities in this phase domain. So now going back to this impedance control equation that's typically used in these prosthetic controllers. So these 3 parameters, stiffness, equilibrium angle, and damping, are typically tuned. And our goal was to try to kind of reduce the amount of tuning by not having these individual substates that needed to be tuned. So by using this phase variable, we now have, we have a continuous we can create a continuous torque model for what these stiffness, equilibrium angle, and damping parameters should be at each point in phase or the progression of the sit to stand or stand to sit motion. And to do this, we create an optimization problem where we want to minimize our the error between our modeled torque and the experimental torque that we see from our data set. And we add some constraints to this optimization problem, such as that the torque at the ankle and the knee should be 0 when the person's sitting. The torque at the knee should be 0 when the person's standing. And then using this optimization problem, we're able to create these continuous stiffness, equilibrium angle, and damping trajectories. So this is what they look like. And so as you can see, so this phase, basically we see these parameters are continuously varying over the progression of the motion for both the knee and the ankle. And in order to kind of validate this, we looked at the error between our input torque from our data set at each joint and our model torque. And so, for example, for the sit to stand motion, here for each joint, the ankle, this RMSE is the direct comparison between those two torque, the model torque and the experimental torque. And this normalized RMSE is divided by kind of the joint torque standard deviation. So you can think of that as kind of the variability with respect to the data set. So our error is a little more than kind of the variability in the input data set, but not significantly. And so we compare this error in our model using only the sit to stand data, only the stand to sit data, and then combining these two models, and we can see that the combined data does have a slightly increased error for both the ankle and the knee, but it's very minimal. So we use this kind of combined model for our experiment. So we brought in one participant with an above knee amputation to test this, and we compared his this robotic prosthesis with his typical passive prosthesis that he normally wears. So after some acclimation period, first he trained. So we were specifically interested in trying to reduce asymmetry and trying to reduce the time that it took for him to go from sit to stand. So he did 10 minutes of training, trying to reduce this asymmetry. So he had each leg on one force plate, and he was able to see in real time kind of how evenly he was loading both of his legs. So I'll show a quick video of that. So if this bar was kind of in the middle of the screen, that means he was perfectly symmetric. And if it was to the left or the right, then he was loading the left leg or the right leg more than the other. And you can see that it during that video, it largely stayed in the middle of the screen, but there were times when he was asymmetric as well. So after this training period, we took away the visual feedback and then tested our controller compared to the passive prosthesis. So we had a couple different conditions for sit to stand. First, a relaxed condition where we asked our participant to sit and stand at a comfortable pace, kind of focusing on maintaining that symmetry that he had practiced. And then a rapid sit to stand where he was asked to sit and stand 5 times fast as comfortably possible with his hands crossed over his chest. And we compared our powered prosthetic controller compared to his passive device. And so this chart shows how much he was able to reduce the asymmetry in the loading between his two legs. So with the passive prosthesis in yellow and powered prosthesis in blue. And you can see that in all 3 conditions, he was actually able to reduce that asymmetry by about half, which is pretty exciting. And even in this rapid condition where he was told to focus more on timing versus asymmetry, he was still able to, asymmetry reduction still remained. And during this rapid condition where we told him to sit and stand as fast as possible, he was also able to reduce that time required to to stand and then sit back down by an average of 20%. So here's a video of our participant doing that rapid test. And you can see that it looks pretty natural and definitely decrease the time required to complete this task. So our conclusions from this experiment. So this controller that we developed didn't require any tuned impedance parameters. And that has the potential to kind of increase clinical viability because you don't have to spend kind of a lot of time tuning different tasks. We also created this unified sit and stand controller, which can reduce the likelihood of misclassification. If you have two separate modes, you have to then decide which mode that you're in and transition between them. And then our controller also resulted in improvements in this sit to stand asymmetry and timing, and that has the potential to improve quality of life for people with amputation. So I hope I've convinced you the importance of understanding human neuromuscular control in developing these assistive devices, whether they be simple passive devices like this exotendon or complex wearable robots like the knee ankle prosthesis. And in this week-long course that I'll be teaching over the summer, I'm going to focus on kind of understanding the complexities of both human neuromuscular control and assistive device control strategies that interface with the human. Specifically, we're going to focus on human musculoskeletal control, experimental motion tracking, and device sensing and control. And we'll also be learning about this material through OpenSim, which is an open source musculoskeletal modeling software that was used in both these projects that I mentioned today. So I hope to see some of you in my course over the summer. And lastly, I'd like to thank all of my co-authors and funding sources for these two projects that I discussed today. Thank you.
Muchas gracias, doctora Welker, por la presentación. Ahora queremos invitarlos a todos a el espacio de preguntas. Recuerden que nos pueden escribir a través del chat o levantar la mano para comentarnos las dudas o inquietudes que tienen acerca de la presentación. Adelante, Luis Felipe Giraldo.
Hi, Cara. Thank you very much for your presentation. I think it's a pretty exciting research that you are doing. I have a couple of questions. One is when you designed the controller in the second project that you showed, you have to tune that controller for each one of the subjects. So you have one subject and then you have to tune a controller so that controller adapts to that subject, or the parameters that you tune it works across subjects.
So the goal of the controller that I was discussing was to kind of eliminate this tuning. So previous controllers that need to tune those parameters for each specific subject, but this controller kind of used group average data to kind of figure out what kind of good parameters, good kind of general parameters would be for the sit to stand motion. I think future work would then focus on kind of how to take this generally good starting controller and then tune for that subject kind of in a time efficient way. But currently, the current approaches are not done in a time efficient way.
Okay. And the second question is how much that leg cost? Because I would like to know if that's affordable in a country like Colombia.
Right. I would say it's probably not, given that it's not approved even in the US for like FDA. The FDA hasn't decided that it's like worth paying for insurance. I would guess that it's probably $30,000 to $40,000.
Okay. But for research purposes, is it available to buy that kind of leg so we can do some experiments with leg or something like that?
Yeah. So the specific leg that I showed is not the kind of the CAD modeling and the design isn't freely available, but there's actually another leg that we work with here at Michigan called the open source leg.
Oh yeah.
Yeah, so that one is much more feasible for example, if you all wanted to kind of, I know the professor working on it is working with people in multiple different countries and definitely trying to make it kind of easy to not only build, but to kind of build novel controllers off of.
Okay, nice, awesome. Okay, thank you very much, Cara.
Carlos Francisco también tiene la mano levantada. Adelante.
Gracias, María José. Tengo la cámara desactivada, pero no hay problema. No me deja activarla, pero no hay problema.
Está bien.
Thanks, Cara. Thanks, Cara, for your talk. I have a question regarding, a momentico. Okay, thank you. I have a question regarding the acceptance of the users of this kind of technology. Let's say, how hard is for them to train with the processes? How hard for them are the use of these processes, and it has to do something with the controller properties or design, let's say?
Right. Yeah, that's a really good question. So I think this user that I showed in this video has worked with us for, I guess, almost a year now on kind of testing our different controllers, and which I think his trust in the leg is like slowly building over time. But the videos that I showed for sit to stand, for example, that was the first time that he had tested that specific controller. So I think, yeah, it's definitely training is, and kind of user trust in the devices is definitely very important, that a very important topic that isn't necessarily looked into enough by researchers, especially I guess going back to the running device, even such like a simple device as that, when we first put it on users, it didn't actually help them to save energy, but over time they were able to adapt to it, and it actually helped.
Thank you. I guess it's the technology causes fatigue on the users, maybe.
Right. Yeah. And I'm interested in these types of questions, like characterizing kind of cognitive load. There's some kind of initial work being done on kind of the effect of wearing like an exoskeleton or a robotic prosthesis on kind of secondary like mental tasks that you need to do while you're walking, and how that affects it.
Well, thank you. Thank you very much.
Tenemos más preguntas de otro de nuestros participantes. Si es así, pueden escribirlas o activar el micrófono y decirla a nuestra conferencista. Cristian Javier, adelante.
Hola, gracias. Cara, voy a hacerte mi pregunta en español para poder hacerla mejor, ¿te parece?
Sí, está bien, está bien.
Sí, que lo hablamos al inicio y vale. No sé, ya estoy en el laboratorio, perdón.
No problema.
Estaba viendo un poco los sistemas que desarrollan y veo muchos son muy grandes en algunos momentos y da la sensación de que son pesados. No sé si nos puedes comentar un poquito sobre esas limitaciones de peso que tienen y sobre qué tipo de motores podrían servir, pensando también en el torque que son necesarios sí, para el diseño de estos dispositivos.
Sí. I'm going to answer. Can I answer that in English? Is that okay? Yeah, I think that's a really good point. So yeah, the goal in the design of this leg that I showed in these videos was to make it kind of the same mass as what a typical human leg would be. And I think it's that is true if it's a larger human leg, but for smaller participants that are wearing it, it's definitely heavier than their biological leg and also significantly heavier than their passive device. So I think that definitely limits what we kind of the results that we're going to see with these control strategies. I think kind of taking the principles that we learn from this device and kind of implementing them on, I mean, hopefully in the future they can be implemented on kind of more kind of commercially ready devices that we don't really have the bandwidth to build here. But yeah, and I guess another reason why that leg is so heavy is because it was built kind of with the motors have like a very low gear ratio to kind of better mimic the kind of disturbance response of like a normal human leg. So there's some trade-offs in kind of that disturbance response versus the mass of the leg.
Thank you, Cara.
Mm-hmm.
Nice presentation.
Thank you.
Bueno, muchísimas gracias a las personas que nos acompañaron en este webinar. Para finalizar, quisiera darle la palabra al profesor Luis Felipe Giraldo, quien nos tiene una importante invitación.
Gracias, María José. Creo que podemos proyectar la información del curso, por favor. O la proyecto yo. Eso. Quería invitar a todos los estudiantes que están en este webinar a tomar el curso que la profesora Cara va a dictar de junio 10 al junio 17. Precisamente como Cara les comentaba, ella va a hablar sobre el diseño de todos estos dispositivos que asisten el movimiento humano. En profundidad va a ser un curso de una semana y un día, donde Cara pues va a hablar sobre esto, sobre las herramientas computacionales que se utilizan para diseñar este tipo de dispositivos. Y vamos a estar junto con el profesor Cristian Cifuentes y Carlos Francisco ahí también apoyando este curso. Este curso para los estudiantes de pregrado les vale como curso electivo de facultad o curso electivo de programa, y a los estudiantes de maestría, tanto de ingeniería mecánica, ingeniería eléctrica, electrónica o ingeniería biomédica, a ellos les vale como cursos selectivos de ya sea de otra maestría o cursos de profundización. Eso hay que discutirlo con sus coordinadores, pero hacer un curso con los 3 códigos de los 3 departamentos, entonces ustedes pueden inscribirlo en diferentes partes de la estructura de su maestría. Entonces, una invitación a tomar el curso, aprovechar que la profesora pues, es investigadora top en el área y es un área que está surgiendo y que en unos años va a tomar una fuerza impresionante. Entonces, cordialmente invitados, cualquier información. Entonces, está la información en la página web que se les va a enviar ahí yo no sé si por el chat podemos enviar la página web del curso. Bueno, ahí en ingeniería.uniandes.edu.co también pueden encontrar toda la información en la página web con los temas, los detalles del curso. Igual estamos a su disposición, cualquier información que tengan. El profe Carlos Pacho tiene una pregunta.
Sí, bueno, más que una pregunta, quería reforzar una idea. Es que el curso lo hemos diseñado entre los 3 departamentos y es evidente que los estudiantes de una de las disciplinas pues eventualmente puedan sentir que no tienen algunas de las, digamos, de los conceptos que vamos a usar durante el curso, pero realmente al inicio del curso vamos a estar los profesores Cristian, Luis Felipe y yo dando unas sesiones especiales sobre los temas que pueden ser relevantes de las disciplinas nuestras asociadas con el curso, de tal manera que pues no se vuelva un hándicap para ninguno. Yo creo que para ninguno de los estudiantes nuestros pues seguramente va a tener un poquito más de fortaleza en unos de los temas, pero pues la idea es que aprenda justamente sobre todos los temas en simultánea. Entonces pues vamos a, digámoslo así, no tiene un prerequisito especial de ninguna de las carreras ni nada de esto. Entonces pues quería pues reforzar la idea de la invitación con este mensaje y pues pedirles a los que asistieron que les cuenten a sus amigos que puedan estar interesados que, bueno, pues que vamos a dictar el curso y pues la modalidad que va a ser y pues lo interesante que puede resultar.
Perfecto. Muchas
Así
gracias.
es. Así es, en el chat ya se compartió la página web sobre el curso donde pueden ahondar en la información, en las fechas, los costos, se realizará de manera presencial y también pueden escribirnos ante cualquier duda que tengan. Les agradecemos a todos los participantes por conectarse hoy a este webinar. Recuerden que también les haremos llegar las memorias de esta charla a través de su correo electrónico. Un feliz resto de
María
tarde
José,
a todos.
Cristian levantó la mano.
Ay, cuéntanos, Cristian.
Sí, no,
Adelante.
perdón, era algo simplemente para complementar lo que han dicho, es un poco relacionado con lo que me han preguntado a mis estudiantes que interesados en el curso y es qué tantos conocimientos de base necesitan. Algunos tenían preocupación sobre, no sé, qué tanto MATLAB, qué tanto OpenSim. Nosotros vamos a nivelar ciertas cosas en una parte como preliminar del curso que tomamos los profesores uniandes para pues como que cubrir lo mínimo que se puede necesitar para el curso. Más allá creo que no sé si Cara podría decirnos si hay algo muy particular que se requiera, pero yo siento que será algo como muy abierto como lo habíamos pensado.
Sí, es muy
Como para
flexible.
resolver esa duda que muchos estudiantes me han plasmado.
Sí, voy a intentar como comenzar este curso como un nivel que todos pueden entender como un nivel básico, pero también esos profesores van a ayudarme para que todos puedan tener esta información que posiblemente necesitas antes del curso.
Perfecto, sí. Entonces, muy flexibles en los prerequisitos. Ok, listo, María José.
Listo, entonces es un curso para todos los que les llame la atención este tema en realidad. Y sin temor a los conocimientos que requieran, pues los invitamos a conocer más y a escribirse y los esperamos en junio en el curso. Ahora sí.
María José, alguien pregunta si la grabación del video va a quedar en algún lado.
Sí, la subiremos a nuestros canales de YouTube y se las haremos llegar a través de sus correos electrónicos con el que se inscribieron a este webinar.
Perfecto. Muchas gracias, María José.
No, muchísimas gracias a ustedes, a todos los que se conectaron y un feliz resto de tarde para todos.
Okay. Cara, thank you very
Muchas
much
gracias.
for being with
Sí,
us.
muchas gracias por tenerme.
Bye, Cara. Thank you.
Luego.